Hi everyone, and welcome back to another AP Calculus video. Today we're going to talk about a little topic called L'Hopital's rule. And even though this video is labeled for BC Calculus, this is actually an AB topic. It just happens to show up in both places. So L'Hopital's rule is a rule that was developed when we have a situation where we have the limit of a function, no graph, and algebraically it's just a pain in the butt. So for example, if I have this problem here, the limit as x approaches 0. What happens is when I plug in and use substitution, I get the square root of 1 plus 0 minus 1 all over 0. And I get 0 in the numerator and I get 0 in the denominator. Now, we might be tempted here to write down equals 0 over 0. But I'm going to tell you right now that that is a big fat no-no. Do not ever say equals 0 over 0. Or if you do, you put an x through it immediately. And here's why. 0 over 0 is not an actual number. When you say that something is equal to something, you need to be able to say that it's equal to a value or equal to a number. Never ever say equals 0 over 0. Another similar problem is that if we were to approach a different number like infinity, and we would get a similar situation where we would have infinity divided by infinity. Well, infinity is a concept, not a number. So when we're talking about infinities, we can't say equals an infinity or equals infinity over infinity. And as a matter of fact, we have a vocabulary word to describe what's happening here. And what we're getting here is something called the indeterminate form. And what the indeterminate form is it's a form that we get when we end up with a ratio of two equations. In most cases, there are actually seven forms of the indeterminate form. But the kind that we're going to use here today and see here today is when we have a ratio of two equations and they both either approach infinity or 0, the same thing, not one and the other, as x approaches some value. We call this the indeterminate form. So we end up with 0 over 0 or infinity over infinity. Now, little side note here, when you end up with something like this where you have 0 over infinity, that's okay. It's equal to 0. Or when you have infinity, if you have infinity divided by 0, so to speak, then we would say that this limit is approaching infinity. And remember, limits are not about actually finding concrete values. Limits are about concepts. Conceptually speaking, if I get a limit that's 0 divided by infinity after substitution, really what this is saying is I'm not getting 0, I'm getting something super tiny divided by something super big. Well, when you have a super tiny number divided by a ginormous number, it's going to turn into 0. So that's why when we get 0 in the numerator and infinity in the denominator, we interpret it as being 0. Similarly, when we have infinity over 0, when we're evaluating the limit of a ratio, really what we're saying is, hey, we've got something super huge divided by something super small. And as the top gets bigger and bigger and bigger and the bottom gets smaller and smaller and smaller, well, then we approach a larger and larger value. So we would interpret that limit as approaching infinity. So remember, when we get a 0 and an infinity, think about it, it's not as 0 or infinity, but just as a really small number and a really big number. And you'll often be able to kind of power your way through and interpret your result. But we have 7 types of indeterminate forms. And really what's happening here when I explore these 7 indeterminate forms is I have to understand that when I'm doing a limit, in particular, 0 and infinity are not actual values that I should be getting. 0 and infinity are the numbers that that part of the equation is approaching. So 0 over 0 means we have something really small divided by something else really small. And because they're getting smaller and smaller, and because it may not actually equal 0, it might, but it may not, we don't know. We're saying we're approaching something super tiny and we're approaching something else super tiny. And when we divide them together, we don't know what's happening because they're so tiny. Same thing is true when we have infinity divided by infinity. Infinity is a concept. Just like when we're dealing with limits, 0 is actually a concept, not an actual number. So the concept of a number when I get infinity over infinity is that I have this conceptually huge number divided by this other conceptually huge number. And we need to understand that they may not be the same. The numerator may be approaching infinity way faster than the denominator. or vice versa. So what we need to do is we need to think about these not in terms of their actual values, but we need to think about, well, if I get infinity over infinity or 0 over 0, that means that my function is approaching those numbers. And if one function is approaching them faster than the other, well, then I can kind of maybe get a better picture of what's going to happen. So we have other indeterminate forms here as well, and we'll get into these more. We're going to actually see this later on. This is a common one that we might see, and this actually is another common one too. These other two, 1 to the infinity, 0 to the 0, it's good to know that they are indeterminate, but and it looks like I'm missing one too. 1, 2, 3, 4, 5, 6. There is a 7th. I'll find it. And maybe it's like infinity to the infinity or infinity to the 0. I'm not sure. I must have left it out. But in any case, we don't see them a lot, but they do exist. But what we're going to do here is we're going to focus on these guys. And when we have a ratio, what we can do is we can say, well, maybe one is approaching 0 faster than the other, or maybe one is approaching infinity faster than the other. And so what L'Hopital did was he said, well, because we're approaching these values at potentially different rates, why don't I just compare the rates? And in calculus, we call a rate a derivative. And so what he did was he said, okay, if I have the limit as x approaches a of some function compared to another, so this is called a rational function, so it has to be a fraction. He said, well, if the limit as x approaches a of f of x equals 0 or infinity, so that's the numerator, right? So he is noting this. He said, okay, the limit of the numerator is 0, for example. And then he said, and the limit of the denominator is also 0 or infinity. Okay. Then he said, okay, if that's the case, then I'm going to do the limits of the rates. Maybe one's changing faster than the other. And so the rate is the derivative. So he said, well, if I have this special situation where the top and the bottom are both approaching either 0 or infinity, then we just compare the limits of the derivatives. And it works really well. And there is a great proof to this that you guys can look up. I don't have the time or the wherewithal to do it at this moment or to include it in this video, but that sounds like a great Dorsing Proves It video. We'll see if that comes its way. But basically, you can use L'Hopital's rule, but only after exhausting other algebraic options like factoring and simplification. So this is, and by the way, here's L'Hopital. Look at his hair. He's got some, it's a great wig. It's great. Well done. But he was this French guy, Guillaume de L'Hopital. And L'Hopital means the hospital in French, so there you go. Let's see what it looks like. So let's revisit this. So when I use L'Hopital's rule, when I invoke L'Hopital's rule, right, I want to first state the conditions present. So when I plug 0 in, I'm going to be really tempted to say, oh, it's 0 over 0, but I'm going to put an x through that immediately. Do not put, you just x it out. Because if you do that on a free response, you will lose a point because 0 over 0 is not a number. Now, if you just have it floating around in your paper, that's fine. But if you have an equal sign with it, cross it out. So I would just get in the habit when you have 0 over 0 or infinity over infinity, just put an x over it. Boom, done. Now what we need to do is we need to state what just happened. So we're going to say that the limit as x approaches 0, and I'm going to give the numerator, 1 plus x minus 1 equals 0. Then we're going to say that the limit as x approaches 0, we have to give this, is 0. So I've taken the numerator and the denominator, and I've separated them, and I've said, hey, here's what just happened. Now I'm going to show the derivatives. So I'm going to say the limit as x approaches 0 of this function equals the limit as x approaches 0. Now I'm going to do the derivative, so the bottom's easy. But the top part has this square root, so I'm going to have 1 plus x minus 1. So the derivative of that is going to be 1/2. So that's y prime. Label everything, right? 1 plus x to the negative 1/2. And then the 1 goes away. No chain rule, good deal. So 1/2, 1 plus x to the negative 1/2. Okay, well now I'm going to plug everything in. So here goes. Actually, I'm just going to use my substitution. So I'm going to have 1/2, 1 plus 0 to the negative 1/2 over 1. Hey, that's going to be 1 to the negative 1/2. That's 1, so 1/2. Ta-da! I've just used L'Hopital's rule. I did the derivative of the top, derivative of the bottom. But you always, always, always need to show these three things. You need to state the conditions. So this is number 1. Number 2, you need to show the derivatives using limit notation. So this right here is number 2. So you need to show that you're using L'Hopital's rule. You don't even have to call it L'Hopital's rule. And then number 3, you have to evaluate it and get to your answer. So you have to do these 3 steps. So let's try another one. And if you want to pause the video and give it a try, you go right ahead. Now, I know we're going to have to use L'Hopital's rule because this is the lesson on L'Hopital's rule. And I know that when I put 0 in, I'm going to get 1 minus 1 over 0. I'm going to get 0 over 0. And as soon as I get that, I'm just going to put an x through it. Boom. X it out. Do not say equals. You put an x right through that. That is not allowed on your paper. So now we know we're going to have to use L'Hopital's rule. So I'm going to go ahead and I'm going to do number 1. The limit as x approaches 0 of 1 minus cosine of x equals 0. I'm going to show that the numerator goes to 0. I'm going to show that the denominator goes to 0. I'm just going to state that. I don't even need to show that I'm plugging it in. I did it up here already. And I x'd out my 0 over 0 so I don't get dinged on my AP exam. So now I'm going to state them separately. So that's number 1. Number 2, I'm going to do the limit as x approaches 0. I'm going to do the derivatives. So here we go. My wheel of signs. Okay, derivatives go clockwise. So I'm going to have negative cosine. So this is just going to be sine. So sine of x over 1 plus 2x. All right, now I'm going to evaluate this. Okay, the sine of 0 is 0. And then when I put 0 in, I get 0 over 1. Oh, that's just 0. Okay, done. I've gotten a number. I'm done. As long as I don't get 0 over 0 again or, anything like that. So this is nice and easy. Remember, step 1, separate the numerator and the denominator. Say that they each approach 0 separately, independently of each other. The second thing, show the derivatives. Third thing, evaluate. So let's do another one. Here we go. Ooh, we've seen this one before. Sine of x over x. The answer should be 1. We should remember this. This is one of those graphs where we goes like this and there's a little hole up there. So we know that this limit is 1. This is something we should remember. But let's use L'Hopital's rule and prove it. So here's the problem. When we put in 0, we get 0 over 0. Oh, and I'm just x it out. Oh, x it out. Leave it alone. Like, don't leave it on your paper. It's ugly. It's going to cause you problems and pain and lose you points. X it out. 0 over 0. No, thank you. So now I'm going to do this separately. Limit as x approaches 0 of sine of x equals 0. The limit as x approaches 0 of x equals 0. Okay, I've set the stage. Now I'm going to use L'Hopital's rule. The limit as x approaches 0 of cosine of x over 1 equals, 1 over 1. It's 1. We can use L'Hopital's rule to find this answer. Ta-da! We knew it was 1. L'Hopital helped us get it. Let's do another one. This time we're going to approach infinity. Oh my goodness. Well, okay, as I'm doing my limit, because remember, we don't always know that it's going to be a L'Hopital problem, right? It could just be any limit. So when I plug this in, the limit is n natural log goes all the way for forever. Oh, it's infinity. Oh, infinity over infinity. Oh no, I can't leave that on my paper. X it out. You cannot leave that on there. You cannot say equals infinity over infinity. Put an x through it. Boom. Now we're going to use L'Hopital's rule, because remember, when we get this indeterminate form, we can set it up, and now I'm going to do the same thing, but this time I'm approaching infinity. Ta-da! And then the limits as x approaches infinity of 2 square root of x also equals infinity. So I've separated them out. This time we're just equaling infinity instead of 0, but the steps are the same. So now I'm going to do the limit as x approaches infinity. I'm going to show the derivatives. Natural log, that derivative is 1 over x. Ooh, this derivative, 2 times x to the 1/2. So the derivative would be 1/2 times 2. Oh, that's nice. X to the negative 1/2. Oh, x to the negative 1/2. Okay, I got this. So now I'm gonna do my limit as x approaches infinity. Let's see. This becomes 1 over infinity. That's going to be 0. Oh, this becomes, I'm going to have a problem here again, aren't I? So when I have x to the negative 1/2, I need to remember that this is 1 over the square root of x. So what I'm going to end up having again is 0 over 0. Now, one of the problems I'm going to run into is anytime I have fractional exponents or things involving radicals, there's really no good way to L'Hopital your way out of it. So what we'll need to do from time to time is we're going to need to do some algebra. So I'm going to back up a little bit, and we're going to treat this problem, we're going to rewrite it, and we're going to say, well, it's the limit as x approaches infinity of 1 over x and then 1 over the square root of x. Now I'm going to simplify. I'm going to get rid of this fraction within a fraction, and I'm going to change it to this. The limit as x approaches infinity, and I'm going to flip this denominator and rewrite it as the square root of x over x. Now anytime I have square roots in the top and things that are not square roots in the bottom, here I could actually L'Hopital my way kind of out of this one, because I'm going to get infinity over infinity again. And it is possible to use L'Hopital at this point, but another way to treat this is to algebra my way out of this. And so what I'm going to do is I'm going to rewrite it like this. The square root of x, and I'm going to change this denominator to the square root of x squared. So a little trick that I know is to put everything under one radical. Then you get x over x squared. And then when we simplify, and we're going to get 0. Now, previously, had we kind of done some other manipulations here, you might have noticed that we got 0 times infinity. Well, 0 times infinity, let's go back here. The trouble with 0 times infinity is that we need to remember that 0 times infinity always gives us an indeterminate form. So remember, the infinity often comes from 1 over 0, or the 0 often comes from 1 over infinity. So essentially what we end up getting is 1 over infinity times infinity, which is infinity over infinity. So we still get this indeterminate form. 0 times infinity is just another way to write these 0 over zeros or infinity over infinity. So it's really important that we understand that 0 times infinity is another it's another form of the indeterminate form. It doesn't give us any information, simply because we can think of the 0 and the infinity coming from 1 over the other part. So when we have a problem like this, we may need to do a little bit of algebra to get our way out of it. Now, had I done some algebra here, had I used L'Hopital's rule, this would have just turned into the limit as x approaches infinity of 1/2 x to the negative 1/2 over 1, which would have been the limit as x approaches infinity of 1 over 2 square root of x, which would have gotten us to 0 as well. So there's often more than one way to approach a problem. Whether you're algebraing your way through it or L'Hopitaling your way through it, remember that, L'Hopital is a wonderful tool, but we have to kind of make sure that we're using it appropriately. We don't want to use it in a place where it's not going to produce a result, or it's going to continue to give us an indeterminate form. So you may need to do a little bit of algebra before you can proceed and move forward. We can also take a look at L'Hopital's rule in that we can use it multiple times. So in the example we just did, you saw that I was able to apply L'Hopital's rule a second time. And that is a wonderful part about L'Hopital's rule, is that you can apply it multiple times if you continue to get an indeterminate form. So for example, if I want to evaluate this guy here, I know that when I plug in 0, I'm going to get 0. over 0, but I'm going to X that out right away because I'm not allowed to leave that on my paper. And I'm going to say, okay, well, the limit as x approaches 0, I'm going to write out the numerator equals 0. The limit of the denominator equals 0. And now I've set myself up. I can apply L'Hopital's rule, so I'm going to go ahead and do my derivatives. I'm going to say the limit as x approaches 0. And I'm going to say 1/2 times x plus, or 1 plus x to the negative 1/2 minus 1/2 all over 2x. Uh-oh, I'm going to get 0. Uh-oh, when I plug this in, yikes, I get 1. Oh gosh, I get 0 over 0 again, but I'm going to X it right out because I'm not allowed to leave that on my paper. So all I'm going to do is I'm going to take the second derivative. So L'Hopital's rule can be applied as many times as you need to if you continue to get indeterminate forms. So I'm going to go ahead and I'm going to state my thing. I'm going to say, okay, well, the limit, I have to do this, as x approaches 0 of 1/2 1 plus x. That one is 0. And then the limit as x approaches 0 of 2x was also 0. So now I have to restate why I'm using L'Hopital. And now I'm going to do the derivatives. So this will become negative 1/4 1 plus x negative 3/2 all over 2. And when I put in 0, I get negative 1/4 over 2. I get negative 1/8. So there's my limit. So it is possible to apply L'Hopital's rule more than once. The last thing that I'll talk about here with L'Hopital's rule is we can also use it for one-sided limits. So let's review some one-sided limits here. So remember, a one-sided limit has the little plus or the minus. So this right here, this means we're approaching 0 from the right. So from the right-hand side, what am I trying to become? Well, when I do this, I get, oh, surprise, surprise, 0 over 0, and then I'm going to put an x through it because I'm not allowed to leave that on my paper. And then I'm going to state the limit as x approaches 0 from the right of sine of x is 0. The limit as x approaches 0 from the right of x squared is also 0. So now I've stated my facts. Now I can use L'Hopital's rule. The limit as x approaches 0 from the right, all right, cosine of x over 2x. From the right, cosine becomes 1, and then this becomes 0. So, oh, it's infinity. So 1 divided by 0 gives me infinity for this one. So this one has a limit approaching infinity. Now, one thing I will make sure that we understand here is that we are approaching this from the right. If we were going to approach from the left, suppose we want the limit from the left. Oh, surprise, surprise. Here's what's happening. I'm going to still get 0 over 0, and I'm going to X it out, and I'm going to state my things. I'm going to say the limit as x approaches 0 from the left of sine of x is 0, and the limit as x approaches 0 from the left of x squared is also 0. I'm going to state those things, but now when I go and do my derivatives and I evaluate, watch what happens. So I'm still going to get cosine of x over 2x. The limit as we approach 0 is 1 in the top, but then here in the bottom, we have to understand that when I'm approaching 0 from the left, so here's 0, I'm going to have negative numbers and I'm going to have positive numbers. If I'm approaching 0 from the left, that means all these x's are negative values that I'm plugging in. So what's happening is I'm plugging in smaller and smaller and smaller negative values. And when you have 2 times a negative number, you're going to get a negative infinity in the bottom. Or sorry, a negative, you're going to have, not negative infinity, I'm jumping ahead of myself. You're going to have a really small negative number. So some small negative value close to 0. Well, 1 divided by a really small negative value means that I'm approaching negative infinity. So it's really important to understand that one-sided limits, if we get an infinity or a negative infinity, it's possible you may need to think your way through it and understand that, oh, from the left we're plugging in negative values, so here we're approaching negative infinity. You really have to think about the numbers you're plugging in. Remember, a limit is asking, what is our value approaching? So from the right, remember here, it was okay because we were coming from the right side. We had positive values. So we were plugging in smaller and smaller positive values in for that x. So we had a positive 0. So sometimes what I'll do is I'll say, oh, it's positive 0. And then down here I'll write down like negative 0. That's just kind of how I kind of think my way through it. It's a really negative number. So negative infinity from the left, positive infinity from the right. And if we graphed it, we would see that that was the case. So hopefully this has provided a good review of limits and how they operate. Get it all on the screen for you. And the more you practice, the more it's going to come back to you. And sometimes you can be a little rusty. Maybe you didn't grasp limits firmly the first time through. That's a really common thing. Remember, it's all about algebraic manipulation. And now we're just adding another tool to our tool belt. When we get that indeterminate form, we cross it off, and then we state the numerator and the denominator separately. And then we go ahead and proceed and use L'Hopital's rule and make sure we express the derivatives within that limit notation and then go ahead and evaluate. So we can use L'Hopital's rule multiple times, whether we're approaching a number, whether we're approaching infinity, it doesn't matter. L'Hopital's rule is a really versatile tool that we have for evaluating these limits. Keep practicing. The more limits you try, the more algebra that you practice with, the better you're going to get. It takes time, it takes practice. Keep at it. You can do this. You've got this.